this Massimo, got his PhD from Pisa in 1986, and then his first postdoc was at Rutgers. Then he went back to Europe. He was a fellow at the European Space Observatory, ESO, Southern Observatory, which is, of course, in Munich, right? As the name says. Then he got a position in Pisa in 92, but actually in 95 he moved to the STSCI, the Space Telescope Science Institute, in Baltimore, across the street from Johns Hopkins, essentially.
Yes.
Here, where he's now an astronomer with tenure, and very recently, not so many months ago, he became the head of the James Webb Mission Office, so the science part of the James Webb Telescope. And we talk today about reionization and fast galaxies.
It's a pleasure to be here. It's a small tradition every 3 or 4 years, or I have the pleasure of being invited. What I'm going to talk about today is work that we did in collaboration with some postdocs and students, and within also very large teams that worked on the ultra deep fields. And of course, that's Hubble as it is now, and this is how James Webb will look.
That's not to scale, no? On the first extra
No, it's a little bit far off. Hubble is pretty large. It's as big as a bus. So it's 2.4 meters here to here, but it's almost 4 meters here to there. And this mirror is 6.5 meters flat to flat. So Hubble is a big telescope. And in fact, James Webb is lighter than Hubble, despite having much more collecting area. So I'll try to argue when reionization happens. And reionization in our jargon is the reionization of hydrogen in the universe, because reionization of helium happens at a different time, and it's, although still debated, it's better constrained. I'll describe what deep fields with Hubble can do in this field, what they imply for reionization. I'll say a few things about how we think that the first objects form, and speculate on what we will be able to do with existing and future observatories. So there was a big boost in this field with the Sloan and Digital Sky survey as they started to find...
Could you explain, for those of us who are ignorant, reionization?
Okay, so I wonder if I added a plot, but no, I didn't. So after recombination at about redshift 1300, all matter in the universe recombines. The universe becomes almost neutral, almost completely neutral.
400,000?
And it's a redshift, yeah, it's about 300,000 years, and that's when the cosmic effectively radiation decouples from baryons, and you have the cosmic microwave background radiation that is released. So the universe after that is the baryons are essentially neutral. But when we look at objects at a very low redshift, we see that what we call the intergalactic medium, this is the gas distributed between galaxies, is actually ionized. So at some point, after redshift 1300 and before a redshift that I'll describe here, 6-ish, something reionizes all hydrogen in the universe.
How do we know that there wasn't just a small amount that remained ionized?
Well, there are many ways. One is that the microwave experiments like WMAP can measure the optical depth in free electron to the cosmic microwave background, and we know that if you use the very simple-minded model, you would have reionization at redshift 10. Probably instead of it being an instantaneous process, is long, but you know that you don't have a lot of free electrons at higher redshift.
So it had to reionize.
It had to reionize. Also, modeling it it would be very hard to have a non almost complete recombination. It's this brings us a bit away from what I wanted to talk, but if you were using simple arguments like Saha equation, it would be essentially completely neutral. Actually, since in this time you're getting out of equilibrium, you don't get to complete neutrality, and you have to use time-dependent equations, and you find that it's about 2 parts in 10 to the 4. That's the residual ionization. So it's almost completely neutral. So what discovering these quasars allowed us, a quasar is you can think of it as a very bright continuum source at cosmological distance. So something like that allows you to probe matter between you and the object. And what happens is that these are spectra. This is flux as a function of wavelength for a bunch of quasars at the redshifts indicated here. And as you can see, once the redshift is below 6, you see some flux. These are very high signal-to-noise spectra, so these little things are not noise. That's actual signal. There is some flux that is coming out below this little bump, which corresponds to Lyman alpha, the transition from n equal 2 to 1. From 2 to ionized. And that's, this little flux is meaningful. The quasars would have a spectrum then continuous going up. So the reason why instead of seeing that you see these little things is that there are a lot of individual neutral hydrogen clouds between us and the quasar. And of course each of these clouds absorbs hydrogen resonantly at Lyman alpha. And so they cause a big absorption at their redshift, and you have a lot of them spanning a range of redshift, and they build up a lot of absorption. However, if you had a diffuse neutral hydrogen medium, you would have complete absorption. It would look like that. And so you know that at a redshift like this, along this particular line of sight, there is no diffuse neutral hydrogen to a very high limit. Here, there might be. If you see some flux, you know there is no neutral. If you don't see any flux, it depends, in the sense that you could imagine a very large number of discrete clouds that would mimic a neutral medium. So you need to look at many lines of sight, because this effect will depend on the direction you look at, and you need to do detailed modeling as a function of redshift to see if the statistics of the clouds is compatible with seeing a certain complete absorption or not. But a lot of people looked at it, and the qualified conclusion was that probably you were starting to see the end of the reionization of hydrogen at this redshift. So, if the quasar tell us the reionization ends somewhere around 6, but WMAP, as I mentioned just now earlier, would suggest reionization at redshift 10.8, but based on very simple physics of instantaneous reionization, which is not, it's unrealistic. There are additional surveys of a certain type of galaxies that are, somewhere in between. Now, it is possible actually to build toy models that fit all of these constraints. And here, this is the ionization fraction as a function of redshift, and you start from a population of primordial stars. What we call population 3 stars are stars that have the chemical composition coming out of the cosmological nucleosynthesis. So they are essentially just helium and hydrogen and very little traces of other elements. These are very different from the stars around us today. And they are different in properties because as soon as you start adding elements, the way the star cools is very different. So this generation of stars as pre-enriched we have never seen one, but we know they must exist because we have never, the stars we see around us have some chemical content, so somebody must have gone through the cosmological nucleosynthesis, the primordial nucleosynthesis to what we see today. And we call them population 3 stars. So with a contribution from them, a contribution from more regular stars, you can fit all those observations, because the different probes are sensitive to different column densities of neutral hydrogen. So it is likely that the reionization of hydrogen started at some high redshift. It must be greater than 10 if the WMAP measurement is right and the simple instantaneous reionization gives you 10. If you have a diffuse process, in order to have the same optical depth, you need to start early if you want to finish later. And it continued down to some low redshift. So how do we find out who did it? Well, it turns out that when those measurements came out, a new instrument called the Advanced Camera for Surveys had been installed on Hubble. And the reddest band that this instrument could measure effectively probes redshift 6. So it was very compelling to find evidence that reionization might finish at 6, and you just have a brand new instrument that can find galaxies at 6. So the simple idea is that let's count these galaxies and see if they can produce enough ionizing photons to reionize the universe. By the way, why do we care about reionization of the universe? Maybe at some point I should say that too. I wanted to add a slide, and obviously I forgot. But we care, there is a kind of a philosophical reason. Reionization is probably the last global phase transition that the universe undergoes. There is a more practical reason, and that is that reionization affects the formation of very low mass galaxies. Because before reionization, low mass halos, dark halos, the baryons in low mass dark halos are shielded from any ionizing source because of all this neutral hydrogen around. Photons don't get to the halos because they are absorbed somewhere else. And so these small halos have a chance to turn into dwarf galaxies. After reionization, you don't have that shield provided by the diffuse neutral hydrogen, and these dwarf halos actually can photoionize, you lose the gas, and that dwarf galaxy is dead. It's a dark halo without visible baryons. And these has direct implications on the statistics of dark halos that you see or you don't see around nearby galaxies, and can constrain. Yes?
I didn't mean to interrupt mid-sentence. Sorry, why does ionizing the gas kill the galaxy?
Because these low mass halo have very low escape velocities. So once you photoionize the gas will leave the halo.
Okay.
So in terms of these galaxies, for reionization, what sources are included? I mean, is it potential AGN included?
I'll say a little bit more. The consensus that we are coming to is that it is stars that do most of the job.
So stars both during their lives as well as through their deaths. So you have gamma ray bursts, you have had shock breakouts.
Is actually mostly during their lives. And so something like an ultra deep field. So what is this plot? This plot shows the number density of objects per arc minute square on the sky versus the magnitude. This magnitude is a physics, is the answer of an astronomer who actually got his degree in physics to the astronomer's magnitude. So it's defined as minus 2.5 log, base 10 log of the flux in Jansky. And Jansky is a unit of flux density. So this is a magnitude normalized to some rest frame wavelength, which is longer than, non-ionizing, longer than even than Lyman alpha. So if you are imagining a population of galaxies, there will be a curve in this whitish area, or in this plot, certain number of objects per each magnitude. If your population lives in this lower corner, that population doesn't produce, under even the most favorable assumption, enough ionizing photons to ionize all hydrogen in the universe. So your population cannot make it. If you live in this upper area, you can reionize, but you are actually producing, you're so inefficient as an ionizing source that you produce so many metals to produce those ionizing photons that you enrich the intergalactic medium more than the constraints that we see. So this is also a kind of forbidden area. It's forbidden less strongly than this, because here, if you don't have photons, you don't have photons. Here, there are some errors in how well we know the metals in the intergalactic medium, and so this is a softer boundary. But with these two criteria, you conclude that your population reionizing the universe must live in this non-shaded area in the middle. Doing an ultra-deep field with the Hubble, and each of these little L-shaped corners means that you're sensitive to a minimum number density of objects that are no fainter than some other value. So you're sensitive to anything that is to the right and above the L. So you can see the old surveys didn't have a chance to detect reionizers, but an ultra-deep field could have, under some parameters, the chance to detect these galaxies. And this served as a motivation to do the Hubble ultra-deep field that we did a few years ago. And then we have had follow-up studies to go in the infrared to probe higher redshifts once the instruments became available on Hubble. Surveys like an ultra-deep field are what we call pencil beam surveys. You go very, very deep in a very small area. So for certain luminosities of galaxies, you don't have a fair sample of the universe. You have a good number of very faint galaxies, but your bright objects have a low density and are limited by the very low volume spanned by your survey at each redshift slice. And so you need also to do a wide survey, less deep, but with a broader area, to get good statistics on the bright end of the distribution of galaxy luminosities, and we did that too. And how do we
decide where to point? The funny answer is it's carefully chosen random pointing, in the sense that it's random, but among all random pointings, you want to exclude areas where you have extra background from the solar system, the ecliptic, extra background from the galaxy, very bright sources, so and also an area that is technically well observable by major facilities, and so that sort of constrains where you can look. So the technique we use to identify object samples is called Lyman break technique. And the reason is that once you go to this type of objects, they are too faint to take a spectrum. A spectrum would be the truth. You identify lines, you know the redshift, you can go home happy. These objects are too faint to take spectra with present technology, or at least some of them are. So what we do is to use the so-called Lyman break technique. A star-forming galaxy has a spectrum that is roughly flat in these units of nu times f nu. And hydrogen in the objects and in the intervening clouds from us to the objects absorb completely below the Lyman limit, but significantly under Lyman alpha, the spectrum, and you get something that depends on the line of sight, but looks roughly like this. So if you probe with color filters this area before and after Lyman alpha, and then you have a longer color, and you look for objects that are red in the blue, that are red here, a lot more flux here than there, and are roughly flat here, you identify star-forming galaxies at the redshift of interest. In this case, with these filters, it would be 5. If you use these two as the two shortest, it would be 6. And you can kind of model what is your sensitivity.
Why is the spectrum so remarkably flat? Is it some weird coincidence?
No.
Look at it, it's flat, really.
Yeah, it's pretty flat. That's what young stellar populations look like.
Just happens to be, you say.
Yeah.
Well, probably if it wasn't flat, I would be plotting something else, but yes. F nu is a good unit because it's sort of the energy per band. So I think it's a good unit. So these are in the ultra-deep field, the objects that are identified at redshift 6 with their detection signal to noise, the red dots. So you see, and this is the magnitude in the redness filter. So if you wanted to take even not so good spectra of these objects, you would need to integrate the number of hours given here with the largest telescopes that we have now. So this shows, since you have to use pretty dark nights, clear of clouds and so on, 1800 hours is a heck of a lot of time for a ground-based telescope, because of course you can't see a certain point in the sky all year around. And so this is, somewhere between here and here is a practical limit of what even an heroic effort could give you. So you see the majority of the redshift 6 candidates that we detect are actually unreachable from the ground. That's why we need to use the colors to identify the sample, because the spectra would not be obtainable today. We can use Hubble itself to get spectra, and we have done it down to about here. And what we see is that the selection is clean. More than 80% of the objects that we select are actually at the redshift that, and we can try it on more data than this, are actually what we want. But of course, you don't know for sure at magnitudes that are fainter than the faintest you can probe. There are arguments why it should get better, because the interlopers are all lower redshift and are going to be brighter, but it's not measured. JWST will be able to take pretty high signal-to-noise spectra of objects at higher redshift. And this I think is probably a 10,000 second integration, so it's less than 3 hours, so it's pretty easy. And you start to detect lines like this is a forbidden oxygen, this is oxygen 3 and this is oxygen 2, and that's the Lyman alpha. So once you get spectra like these, you can even constrain some of the properties of these objects. In addition to the redshift, you can constrain their metallicity, for instance. That is important. You can derive the luminosity functions of these objects. I won't go into too much details, but there are the typical issues that you encounter in every physics measurement when you try something. You have a lot of observational effects. You need to take into account the error bars. We do some of that by having Monte Carlos, where you sort of see your projected objects, how they would scatter in and out of the sample, and you derive contours with where you measure parameters of the functions that describe the luminosity of galaxies. What we find is that the luminosity of galaxies has a shape roughly like this. This is at 8, for instance. And it's pretty steep at the faint end. This is now the absolute magnitude. And it falls off rapidly at the bright end, but it's pretty steep at the faint end. And in fact, the faint end is so steep that it's often found to be compatible with the slope of -2. -2, in this context, is the logarithmically diverging luminosity slope. So that means that you can hide as much, probably you would call it an infrared divergence. You can hide as much light as you want in dwarf galaxies, depending on how faint you're willing to go before you truncate the luminosity function. So this is an important ingredient for the answer. And this is how stars form in the universe, as far as we can tell. So there is a time, a redshift around 3, where there is the peak of star formation activity in the universe, and then it goes down. So what does this all mean for the reionization of hydrogen? Reionization of hydrogen has a number of issues, and if one wanted to be very critical about this, could describe the field as a field where people go to great length to come out with a nice measurement of a certain flux with small error bars, and then multiply this number, accurately measured number, with two largely unknown quantities to derive what they need. And the two quantities arise mostly because, first of all, we don't know the intrinsic spectrum of the objects that do the job. We can measure their flux in the non-ionizing part of the spectrum, because all the ionizing photons are absorbed on their way, somewhere on their way from there to here. But we want to know how many of those ionizing photons there were. So we need to assume something about the spectral energy distribution. Of course, it's a learned guess. You know, we know what stars can do, we know what AGNs can do. So it's not a complete shot in the dark, but still it involves an extrapolation from what you can measure to something that you can't, by construction, measure because it's absorbed by the intergalactic matter along the line of sight. The second part is that your galaxy, which is this little thing, will have a bunch of stars and will have gas. Part of it is the gas from which those stars formed. So the ionizing photons produced by these stars, some of them will bounce around and ionize the gas in the galaxy itself. So they never make it out to the intergalactic medium. Not only, but some of the ones that do make it out will be absorbed by another cloud. And so in order to reionize the universe, you have inefficiencies. And one way to capture at least the escape here is to introduce the so-called escape fraction, that only a fraction f of the ionizing photons you have actually makes it out. And then you can try different things. Like in the plots that I had initially, they were labeled with two numbers, and one of them was the escape fraction, and one of the curves was characterized by 0.5, which is what you could call the Goldilocks assumption. You know, some escapes, you know, half escapes, half it doesn't. But, you know, that number is not very well constrained. We can measure it in the local universe, but the local universe objects are very different from the objects here. For instance, they have a lot of metals while these objects don't. So, what are the parameters that enable you to reionize the universe? As a function of redshift, and for a given assumption about your stellar population, the metallicity, this is 10 minus 3 solar, this is 1/50 solar, and this is solar. This is a burst, sudden formation of stars, so they are all bright. This is constant star formation for a certain period of time. This is the distribution of masses of stars that you form. And this is a clumping factor that takes into account how clumpy the IgM is for the purpose of reionization. Is essentially rho square mean divided by rho mean square. So what's the departure from uniformity? Because recombinations are a two-body process. You need the proton and the electron to be in the same spot. So they go with the rho squared. So if you have underdensities and overdensities, you recombine more in the overdensity than you lose in the underdensity, and overall you are recombining more. So the escape fractions that you need to reionize with the objects you see go from 19% here to impossible if you had populations like our own galaxy. If you combine all the galaxies we see at 6, 7, and 8, you can barely make it, but with a very unlikely value of the escape fraction. If it's solar, but you can make it if the metallicity is lower. So, we are in the right ballpark. There are physical parameters that give you the result. One of the things we would like to have is the metallicity of these objects to know which of those columns is right. And other things we would like to have is to detect galaxies fainter than the ultra-deep field. Both are things that are technically essentially impossible to do now, because these are the faintest galaxies that we detect with very long exposures with Hubble. Nobody can take a spectrum and measure their metallicity, and nobody can go fainter or by any significant. The James Webb or the extremely large telescopes on the ground could help. So what do we do before these things are available? What you can do...
Excuse me, Massimo, didn't you tell us that this faint end is almost logarithmically divergent, which means that you are extremely sensitive to the assumptions at the faint end? So you don't see them, and how can you predict these numbers if you don't know the faint end of the luminosity function?
Yeah, that's one of the problems.
But then how do you calculate these numbers if you don't
Those
know?
numbers is stopping with the galaxies that I see at the faint
But
end,
this makes
without
no sense.
extrapolation.
But this makes no sense according to what you have said before, right? You know that in fact there are much more galaxies.
Yeah, but yes. Wait, I agree with you. Most likely, this is not a problem because there is no reason why nature should stop making galaxies at the faintest magnitudes that I can measure. There will be some fainter than the faintest I can measure, and those will contribute a large
These
amount.
numbers are meaningless.
No, a lower limit to what you can reionize using objects that you see. So, how can we constrain what we don't see? There are ways to do it. And if I mask in my images all objects I can see with a certain given confidence, and I look at the fluctuations in the background, the fluctuation in the background can have a signature for the population that is not detected. So by taking the power spectrum, for instance, of what I don't see, I can test whether that's compatible with a certain extrapolation for faint galaxies that I don't detect directly, but I can hope to constrain statistically as a sample. So we have tried to do that. John Tonry tried years ago to do it, to measure the distance to galaxies. And what essentially we know pretty well what's the luminosity of a red giant star. So if I want the absolute luminosity, so if I go to a faraway galaxy and I was able to measure the apparent luminosity of a red giant, I would know the distance of that galaxy. How do I measure the luminosity of a single red giant in a distant galaxy? We noticed, essentially, to simplify, that each pixel of your detector, the luminosity is essentially driven by of the order of 100 red giants. So, as long as you get enough photons from each red giant, 7, 10, 15 photons, it doesn't matter that that red giant will not be individually detected with good signal to noise, but the fluctuations in the signal from pixels to pixels will be dominated by the number of red giants rather than the Poisson noise on the photons of the red giant. So essentially you want to measure the square root of the number of red giants per pixel. And as long as you get enough photons from each, you can measure their fluctuation, and that gives you the mean magnitude of a red giant, and then you know the distance. This works, but it's a lot cheaper than what we want to do for two main reasons. One, he had many of the undetected things he wanted to detect per pixel. I have many pixels per galaxy. Even the undetected galaxies are rare compared to the stars in a galaxy over a certain area. And the second is that he knew exactly what's the point spread function, essentially the response, the telescope response to a star, which is essentially a delta function from the point of view of a typical telescope. And so when doing a power spectrum analysis, he knew what K numbers were affected by the star and what were, calibration errors. So he could focus on the part of the K numbers that were affected the most by the signal he wanted to measure. In my case, I don't know that because galaxies come in all sizes. So they can affect a range of K values. So it's a little bit more difficult, and we don't have a final answer, but we have been working on it. And essentially, this is the type of signal we get. This is the difference between these two. If I mask everything down to signal to noise of 3, or everything down to the signal to noise of 5. Of course, if I mask sources down to signal to noise of 3, I'm going to mask also some random fluctuations, because a good number of those are not real objects, are fluctuations, but that's unavoidable. I have to work with what's left. And even at signal to noise 3, 80% of the area of the image is available for the measurement. And so by doing this type of measurements, and we are reanalyzing actually a deeper data set to improve this, we find that the spectrum continues with that steep slope to some fainter magnitudes than the faintest we can measure. So if I had to use at face value the number we derive in this paper, and this is sort of a first exploration, so I wouldn't give a lot of weight. I hope we'll have soon a better measurement. We would go, it's a factor 3 in flux here. We go fainter by enough to actually contribute very significant to the flux. And so if we were in this regime, obviously it would be a lot less of a problem, because an escape fraction of a few percent, 5%, is much more believable. So that part is work in progress. So going back to I showed a version of this plot. As I said, it's possible to build models that fit all observables, but in most of these models, the contribution from this primordial population of stars is small to reionization. And the main reason why it is so, I will skip, I won't describe the figures, but is that a population 3 star forms. In order to form, it has to cool, gas has to cool. It virializes, it warms up, and in order to continue collapsing, needs to cool. It's very hard, and you're talking about mini halos that have virial temperatures of few thousand Kelvin. It's very hard to cool something at few thousand Kelvin using only hydrogen. The reason is that the lowest energy transition that is available has an energy corresponding to more than 10,000 Kelvin. So random motions of your gas are not well coupled to radiation in this regime when your gas is not too warm. When your gas is very warm, they are. But when hydrogen is cold, the atoms bumping into each other don't excite energy level that can be radiated away. So essentially you're not cooling, because in this context cooling means coupling random motions to radiation. So how do you cool? What happens is, even in the primordial universe, you actually form molecular hydrogen, a very tiny fraction of molecular hydrogen, 2 parts per million. Molecular hydrogen, being a molecule, has a truckload of energy levels at low energy. It has vibrations, rotations, and so it can couple to very low energy motions. And molecular hydrogen is the main cooling agent for the first population of stars. Once the metallicity gets to 1,000th that of the sun, even those traces of metals are enough to drive the cooling, because metals, heavier elements, have a lot of energy levels. So they drive the cooling but at these, before you have all those metals, you need molecular hydrogen. Now the problem with molecular hydrogen, there are a lot of complexities, but the problem with molecular hydrogen is that one of these stars is such an efficient ionizer that it dissociates molecular hydrogen in 1,000 of its brother halos. So each star that forms kills 1,000 siblings. So it's a very strong negative feedback mechanism. If you didn't have these, you could reionize maybe just with this population of stars, but because of the negative feedback, the number that you produce remains in check, and they can contribute. But their major contribution is producing those seed metals that allow other populations to form more efficiently by metal cooling. So most likely reionization, I would say, is dominated by the faint galaxies that we know exist and probably exist beyond the limit we see them. And most likely those are also metal poor and so more efficient ionizers, because the more a star is poor in metals, the hotter it is. And this is intuitive because since metals are an effective way to radiate energy, if you don't have metals, you need to run hotter in order to have the same emissivity. So in galaxies near us, the more massive are more metal rich. So the faints are likely to be metal poor, and the two things that together help. And that's what we think reionization will do. So which are, for the first objects, I already mentioned these small halos that cool by molecular hydrogen. And this is the type of feedback you get. When you start having enough, their radiation kills the formation of additional population 3 stars. There are some model dependencies on where exactly stops. And these are 2 models. These models by Haas predicts that we stop at 35. This model by different groups stops at 23, redshift 23, so it's a big difference. But the differences are due to the fact that we don't know exactly how many stars form per halo, what is their mass. So there are some understood differences between these models. There isn't any disagreement on the calculation itself. It's just that there are some assumptions that are not fully understood. So these first stars need to form because they need to produce the metals that we see in even the most metal poor stars around us. We have models of how they form and about their properties. How can we probe those properties? Turns out that even a 300 solar mass star is too faint even for JWST to see, unless you are extraordinarily lucky or they are extraordinarily numerous, which also I would count as lucky. The reason I talk about luck is that in principle, there is no limit to how much gravitational amplification you can get on a star. So if you can get a population 3 star near a caustic of a lensing cluster of galaxies, that star could be amplified by a factor 1,000, and so you could detect it. The likelihood depends on how many there are, and so it is not a guaranteed process, but gravitational lensing, we see it and we use it all the time, but people generally use it to get amplifications of a factor 10, not a factor 1,000. Although there is no reason why 1,000 couldn't work, because a star is sufficiently point-like that can be, it's hard to amplify that much and extend that source because only a subcomponent will be amplified that much and the rest will not. But a star is sufficiently point-like that it could be amplified a lot. So the other way, if we don't get lucky and see them amplified, could be that our models are wrong and they actually form in clusters. If they form in clusters, it would be very easy to see them. By the way, these stars are Eddington limited in their luminosity. They are it's radiation pressure that balances gravity. That means if an object is at the Eddington luminosity, it means that its luminosity is proportional to the mass. So you don't really care what's their mass distribution. You only care about how many solar masses of stars you have. So if you form sufficient solar masses of stars in a spot, you would see them. But a single 300 solar mass, you wouldn't. And by the way, the other properties of being Eddington limited is that it means that the temperature of all of them is the same, and it means that the lifetime of all of them is the same, because the luminosity is essentially m dot, and the mass available is m. So if your m dot is proportional to m, the lifetime is independent of the mass. And this is only true for stars that are Eddington limited. So finally, you could see them if they become supernovae. a star that is radiation supported, if the mass is large enough, could become so hot when it starts burning heavier elements, when it runs out of hydrogen and starts burning heavier elements, that it can undergo a pair instability. This is a pretty spectacular event. It means essentially that it's so hot that it forms electron-positron pairs on its atmosphere. Now, that reduces a lot of radiation support from the atmosphere of the star, so the star collapses because the positron and electrons don't balance it. And what exactly happens depends on exactly the mass. It could bounce, because of course as it contracts it warps up, so there are essentially three possible avenues. It collapses to a black hole and you don't see anything of what it made. It bounces off and produces a pair instability supernova, which is extraordinarily luminous, or it oscillates a little bit before doing one of those two things. If it produces a pair instability supernova, those supernovae would be so bright that JWST would see them at any redshift. The only problem is going to be how rare they are. If they are very rare, we would see it, but we don't know where to look. The other difficulty is that these supernovae are flat for, or at least our models predict that they would be flat for like 200 days. Now, 200 days at redshift 9 is 2,000 days in the observer frame. And detecting something that varies over 2,000 days with a mission that has a lifetime of 5 years is iffy. So you actually would like somebody else to find them before you launch JWST, so that they will know where it is. So, of course, with Galaxies it's going to be easier because they have several stars. We don't know a whole lot about these primordial galaxies. The simulations are not quite ready to form a galaxy from first principle. I was at a conference some time ago, and one of the experts in this field was telling me that the simulation that he was running, which would simulate the necessary scales, small scales, had gotten to redshift 18, and the time on the computer was approaching real time, since the integration was taking longer and longer for each step, because these codes, the more structure you have, the slower they go. They go pretty fast when it's homogeneous. So it's challenging. The first indications, though, are that these objects rapidly get enriched to 10⁻³ solar. So if we take that at face value, it would mean that probably the first galaxies that we see already have a metallicity where most of their stars are forming by metal line cooling. So it could be a pretty efficient, after a first population 3 stars, you would have regular stars from then on. So observations, we detected an object that we thought was a redshift 10. That's how it looks like. It's almost a sad story in the sense that once you go to redshift 10 with Hubble, you're able to detect, or 12, as some people have argued this object is, you're able to detect your object in only one band. That means that you better be sure that you know what your sigma is before saying that that's an X sigma detection. And being sure what your sigma is very tricky because the distribution is non-Gaussian and there are a lot of factors going on. So we concluded that this is a real object. Another group concluded that probably it's real, but it's not clear. It's not at 10 because they look in a different band and it's not seen there either. So it really has to be 12 or a low redshift interloper. That it's always possible, some strange object that has like a strong emission line in the band that we see, and so we get completely confused about its redshift. Unfortunately, Spitzer, which is the far infrared observatory, is not sensitive enough to see it. If this was really 10 or 12, we should see it here given enough sensitivity. This is microns, but it's not, this is 1.6 microns. But this observatory, these are Hubble data. This observatory is not as sensitive, so the fact that we don't see it actually doesn't mean anything. JWST will be able to see it and will be able to do measurements on the first stars, as I mentioned. So concluding, my expectations are that I suspect that JWST, when it launches, reionization will be largely understood in the same sense that we understand weather today. So reionization is a complex phenomenon. We understand weather in the sense we know on large scale what happens, what are the driving factors, and the basic principles. And I think we'll be at that stage with reionization. We probably won't be at the stage, like with weather, of knowing exactly along that line of sight how reionization has occurred and the details of how certain objects will affect exactly how reionization happened. A hard component on identifying who did it is going to be measured in the metal content of galaxies, but this JWST should be able to do. For the first stars, or the first light objects, we think that the first light stars are probably extremely rare, and in order to see them, we can see them as supernovae, and we would benefit from, these are concepts for large area missions that would be able to find some of them that JWST could follow up, or if they are lensed or in small clusters. Current theory predictions don't predict small clusters of these sources in the sense that they can be a small cluster, but the total mass in stars is too small to be detectable. The first galaxies that we'll see will be probably already pre-enriched at that 10⁻³ solar level that I was describing. And of course we need to understand a lot more about the formation of these galaxies before we can say much. This is propaganda on this particular mission, WFIRST. This is the area of the ultra-deep field, and this is the area of a single field that this telescope would map. A version of this was the first priority for the decadal survey for astronomy, because it would also do things for planets and for dark energy. And we may have observed the end of reionization, and we have evidence that it is an extended process. Planck will, will improve the WMAP data and give better constraints on this. With HST, we essentially pushed as much as we can realistically go without using lensing, and further progress may be slow. JWST will be pretty revolutionary in this field, but after all, it was designed as, the old slogan name of JWST was the first light machine, so better be able to do this. And we should be able to detect supernovae from pop-3 stars, especially if somebody else tells us where to look. Thank you. And
any questions? So, Andrei, and then.
Can you explain, so you see something through only one filter. How can you claim that it is a high redshift object?
so it's not the fact that you see it in one filter, it's the fact that you see it in that filter combined to the fact that you don't see anything to very low level in the other filters. So essentially, all the objects we know about would be detected in some of these other filters, because this is, after all, the ultra-deep field. So you are going very deep in those bands where you don't see it. So yes, it's by exclusion. The gotcha is that if you have a very strong emission line that just for something at some other redshift that doesn't have similarly strong emission lines elsewhere, and then line falls in your filter, you could mimic a high redshift object when it could be at any redshift depending on what that line is. Now, I don't think that's very likely, because usually when an object has a very strong emission line, it has some other emission line. And if the strongest emission line doesn't have anything on its left, it's usually Lyman alpha, and that would mean that it is a redshift 10 or 12. So it would have to be an emission line that is not Lyman alpha, and then it would be strange not to see strong emission lines in the other bands.
Maybe it's a signal you like to correct.
Could be. We think it's not, this has been looked in enough detail that we don't think it's a glitch, or we think it's a real physical object. It's not a glitch. But we can't demonstrate that it's a high redshift galaxy until somebody gets the similar sensitivity more in the infrared, and probably that's not going to happen until JWST is launched.
So actually, in terms of the parent stability supernovae, so I wouldn't be so careful in a way, because it could be that the parent stability supernovae from the population 3 stars are very different than some of the models assume.
Yeah.
Because we don't know how they look like.
Yeah.
There was one case where people thought it is a parent stability supernova, 7BI, but that now has been put into question.
Yeah. Yeah.
So it could be that they're actually not that long lasting, not thousands
Yeah.
of days
Yeah.
in observatory. So
Yeah.
the other thing is, in terms of the, I was curious to hear in terms of the update on the JWST, in terms of the solar, it has to have a big shield.
Yes.
In infrared, it has to shield actually from the Earth and from the Sun and so forth. And so just interested to hear what the update on that is, because that's supposed to be huge. I mean, that was my first question. That's supposed to be as big as a football.
Yeah. JWST is
space fully automatically launch itself and open up fully.
JWST sits in an orbit around L2, and L2 is the second Lagrangian point of the Earth-Sun system, and unlike L4 or L5, is a saddle point in the potential, so we need to use fuel to do station keeping or it will drift away. We put it here because one sun shield can shield us from Moon, Earth, and Sun in one shot, so that the telescope can cool to 40 Kelvin. This, in my opinion, the sun shield and the mirror were the two miracles that the mission needed to accomplish in order to work. One of the miracles was the mirror, and that has been achieved. I call it a miracle because you cannot figure a mirror at 40 Kelvin. You can do it in ambient. But it has to have the right shape at 40 Kelvin. So how do you do that? What we did was to pick a material, beryllium, that can be very nicely constrained in its deformation from ambient to 40 Kelvin. And once you know that it's reproducible, you shape it to the wrong shape in ambient that will deform into the right shape at 40 Kelvin. So you imprint the reverse of the deformation. And this has actually been accomplished, and all the mirror segments are in hand and within spec. The second miracle is the sun shield. And there we are making progress. If you're Catholic, you know that it takes 2 miracles to become a saint. But with one, you don't quite make the cut. So we are working on the second one. The second is, there have been a lot of progress, countless, something like this, everything in space, in fact. The cost is not the material, it's the hours of people working on it. And in this context, the hours of people are hours of people doing the modeling for the sun shield. We have computer models. We have tested some of these computer models by building a 1/3 scale prototype that, since we can't deploy it in 0G, in order to make sure that our models describe, can remove the effect of gravity accurately, what we do it is with a 1/3 scale. What we did was to deploy it with G in different directions. So deploy it here, deploy it like this, deploy it like this, and make sure that your model captures exactly what you measure for those deployments. So you sort of validate the model with cases that are testable. But there are still a lot of concerns, and I think the uncertainties now are more on how well it will work rather than.
What is this that Mariam said about football field? I don't understand.
It's a tennis court size. Each of these layers, there are 5 layers. Each of these layers is about the size of a tennis court, and they are about as thin as have the plastic sheet that is used for wrapping in the kitchen.
Saran wrap.
Yeah. And they are made of a special plastic Kapton that is coated. They are coated in a different way, but they are coated with silicon on, most of them are coated with silicon on one side and aluminum on the other, because they are shaped in a way that some photons that get in would actually bounce back out. Everything has been considered to keep the telescope cool. And they are designed in such a way that it's redundant. So it's 5 because 4 wouldn't be enough, 6 is too much. 5 gives you a one failure. 4 would give you what you need, so you have 5 to be able to get where you need to go, even if one gets a little hole or something like that. And they are deployed. I don't know if I have a picture of the rocket, of the stowed configuration. I don't. But they are deployed. The telescope is all wrapped up. So the primary deploys in 3 pieces, the secondary deploys, and in fact the secondary deploys in such a way that it deploys when it's still relatively warm, and when it's cold, the contraction of the metal locks it in place. So the fact that this thing is cooling to extremely low temperature has been used as an opportunity rather than a problem. You save a latch because it latches itself thermally. The sun shield has been looked at many times. Now I would say that the only worry is whether it will be able to cool everything to the temperature that will let us. I'm not so worried about level 1 requirements, which means the signs down to 10 microns. There is some uncertainty on how low the background will be at 20 microns. So some of the mid-infrared might need another little tweak to be safe on that. But in terms of the deployment, there are little technical problems here and there, but sometimes the technical problems don't sound so little. Like there were 4 actuators that somebody didn't quite like, non-explosive actuators, that part of the deployment. And the whole structure had been tested under the assumption that these actuators, when they were released, were giving a burst of acceleration of 500 Gs to everything else. Fine, we can resist that. Somebody in the company decided to do a little tweak in the design of the actuators, thinking that they knew what they were doing, which is always a dangerous assumption. And the new redesigned one gives 2000 Gs or something like that. So that is being reworked. So I'm not saying there are absolutely no problems, but once the project has adequate reserves that we have had since the last replan, you can deal with these problems. The reserves are also there to deal both with the known unknowns, but also with the unknown unknowns that you encounter. So we have been doing that. And so it's 2.5 years that we are meeting milestones and we are on schedule. Clearly, everybody will be happy when it has deployed. But a lot of work went into that, and there is confidence. Even Northrop Grumman claims that they have done like 2,000 deployments in orbit that they cannot tell us about. And so it's hard to verify the number, but they have had some of their teams review our deployment plan to make sure that it fits with what they know. Obviously, this is something that is high visibility for them as well.
I think that at this point we can thank the blessed Stiavelli, since there is already a miracle in the pocket, and continue our discussion on the 6th floor of the
Thank you. By the way, this is Chamber A at Johnson, which is where the Apollo command module was tested. After that, it was made a national monument So we had to get a waiver from the National Park Service to modify it for doing the testing for JWST.
Promise not to destroy it.